Ah, good. Fantastic. Well, okay, I just wanted to welcome everybody to this Black Hole Microstate conference and just say thanks for coming along and thank all the speakers for preparing material. I hope it's good and profitable and useful. And without further ado, I'm going to turn it over to Ben Krapps and talk about slow scrambling in extremal BTZ and microstate geometries. Ben, over to you.
Thanks a lot, Nick, for the invitation. This is actually a project that started while preparing for a panel in the previous black hole microstructure meeting we had back in June, so I'm very happy to report on it. If there was any of you who were in the seminar like a few weeks ago, there will be significant overlap, but okay, I guess the audience will be sufficiently different. Okay, so this will be about a recent paper with Marine de Klerk, Philippe Hacker, Kevin Guillen, and Charles Rabideau. So let me start. Okay, so we'll be studying black holes, which have, as well known, chaotic properties. So they're thermal, and it's known that chaos underlies this behavior. So on the one hand, one has relaxation to thermal equilibrium. On the other hand, there's sensitivity to initial conditions. In a classical system, you would define Lyapunov exponents by looking at phase space trajectories. In quantum systems, it's more complicated to define chaos within a semi-classical approximation. One can simply replace the Poisson brackets by a commutator and consider the growth of the commutator squared in some thermal ensemble. The square is to avoid phase cancellations. And what one does is one takes one operator and evolves it in time, and then the other operator sort of measures to what extent the first operator has spread over the system. So in these semi-classical states, one often has two exponential regimes in the commutator squared. At late times, there are the Ruel resonances, which describe the relaxation of the system. At early times, there's Lyapunov growth. And these two behaviors are quite different. The exponential saturation corresponds, according to ADS-CFT, to quasi-normal mode decay in gravity, and these are easily visible in two-point functions, for instance. On the other hand, the transient Lyapunov growth corresponds to the redshift near the horizon of a black hole. You see here the redshift factor of Schwarzschild time derivative with respect to proper time of an infalling probe, and we will recognize this exponential 2 pi t over beta later on in the talk. So since, okay, first I should say this commutator squared is related to an out of time order correlator. The reason is that if you expand the commutator squared, you get a bunch of terms, and most of them simplify in the large time limit, time large compared to the inverse temperature. That's, for instance, because they might be time ordered, or if you have an operator of the form VWWV, V will create some state that will approximate a thermal state under time evolution, and then the 4-point function will just factorize. But the non-trivial part is this OTOC, where the time ordering is non-standard. And in this regime, it suffices to compute the OTOC in order to have the commutator squared, and that's the object that I will be focusing on in much of this talk. So a difference between the quasi-normal mode decay and the Lyapunov growth is that quasi-normal modes depend on what happens, say, a few Schwarzschild radii away from the horizon, whereas Lyapunov growth really reflects the surface gravity at the horizon. That's why there's this precise exponent 2 pi over beta times pi, which really reflects the temperature at the horizon. So given that this Lyapunov growth is supposed to reflect what happens very close to the horizon. One might ask what happens in horizonless microstates. So I don't think I should motivate the microstate program in this conference. So I'm assuming everybody is at least as familiar with it as I am. So we were wondering, well, if it's true that chaos reflects what happens at the horizon, what will happen if we have states that approximate black holes, but that don't have horizons at all? Now, a complication when you start thinking about this is that microstate geometries have mostly been restricted to extremal black holes, and those have 0 temperature. So this 2 pi over beta in the exponent would just be 0. So one has to be a bit more careful. So what I'll do in this talk is compute OTOCs for extremal black holes and corresponding microstate geometries. And I will use bulk technology for this, and that's also what was in the paper. There is some work in progress that is not finished yet, which I will very briefly mention at the end of the talk, where we try to reproduce these results using CFD computations. All right, so let's talk about how to compute these OTOCs in gravity. So before doing that, let me briefly review what one expects in 2-dimensional CFDs. So let's take operators V and W, where the conformal dimension of both are taken to be large compared to 1, and W is much heavier than V. Then in a nice paper by Roberts and Stanford, it was computed that in the vacuum block approximation, so where one focuses on exchanges of the unit operator and its Virasoro descendants, this normalized OTOC, regularized with these imaginary time shifts epsilon, is given by the following expression. So the epsilons have to do with the regularization parameters. C is the central charge, which I'm taking to be large because I'm thinking of a holographic CFD. And this is what one finds. So you see that if you do a 1 over C expansion, the leading non-trivial term will have the Lyapunov behavior that we recognize from one of the previous slides. This first term corresponds to the exchange of the stress tensor. The original expression here corresponds to all the Virasoro descendants, so products of stress tensors and derivatives thereof. So here you recognize this initial Lyapunov growth, and after this resummation, you also see that if time becomes very large, you will find exponential decay, where the decay constant is no longer set just by the temperature, but also depends on this lightest conformal dimension HV of the lighter operator of the two. But in this talk, I will be mostly focusing on this transient Lyapunov growth, so leading order in the 1 over C expansion. So you can ask, when will this, so this Lyapunov term is assumed to be small initially because 1 over C is a small parameter. But at some point, as you wait long enough, this second term will start competing with the 1 over here, and the time where this competition starts is called the scrambling time, and I've written the expression here. All right, so that was CFD computation. Let me say how to compute this OTOC in gravity. And the trick is to view this OTOC as the overlap of two states. One state is obtained by acting with VW on the thermal field double state. The other one is obtained by acting with WV on the thermal field double state. Now, if I act first with W, I can represent this insertion by propagating it back in time over here. And then it's very straightforward to insert the second insertion V of T3, and the resulting state has a very simple representation at these early times. Conversely, because of the different time ordering in the second state here, it's much more convenient to first propagate V of T1 to late times and then insert W of T2. And this state has an easy representation at late times. And computing the OTOC then amounts to computing the overlap between these two states, which is nothing but computing a 2-to-2 scattering amplitude in this black hole background. So to do this, one can assume that V and W are heavy operators, and which means we're talking about massive fields in the bulk, and then one can do a geodesic approximation. And it turns out that this normalized OTOC can then, to leading order in a saddle point approximation, be written as exponential I delta, where delta is an eikonal phase. It's obtained by computing the gravitational field, which will be a shockwave generated by one of the particles, one of the geodesics, and then integrating it against the stress tensor of the second geodesic and vice versa. So to compute this gravitational fields H mu u, one solves linearized Einstein's equation. And the resulting eikonal phase is then given by G Newton times Mandel's time S. And if you compute this in this way, you find a result proportional to exponential kappa times the time difference, and kappa is nothing but 2 pi over beta, the surface gravity at the horizon. So that's the standard result. So now, because we will be talking about black holes which are extremal, so which are at 0 temperature, I will first, as a warm-up exercise, discuss what happens if you discuss scrambling in vacuum, so temperature 0. So this means we'll be setting beta to infinity. But I cannot just do this in the previous formulae because there we were implicitly assuming that t and x were large compared to beta. So I cannot just set beta to infinity in the exponential and conclude that it's a constant. We need to be a bit more careful. First send beta to infinity and then consider large times. And if you do that exercise, which basically amounts to computing some conformal cross ratio of the insertion points and then being careful about analytic continuations as you cross some branch points in the result. So if you do that, you get a formula which is very similar to what we had before, except that the exponential that was here is replaced by a power law, a quadratic growth in time. Again, I can expand in 1 over c, and the Lyapunov growth is replaced by a t² growth. And this behavior has been dubbed slow scrambling. So now I will move on to computing OTOCs in extremal BTZ geometries. And again, the reason is that these will be the black holes that can be well approximated by interesting microstate geometries. So before we go extremal, let me give you the metric of a rotating BTZ solution. So we have 2 horizons, R plus and R minus. And in the extremal limit, these 2 horizons coincide. I've restored an alias here, and this is the resulting geometry. So in the dual CFT, this extremal BTZ geometry, well, in general, rotating BTZ corresponds to having different left and right moving temperatures. For extremal BTZ, one of those temperatures is 0. My convention is as the left moving temperature, and the right moving temperature is then essentially given by the radius r plus. So to compute the OTOC, I can play the same game as before. I will represent this late time operator phi w of x4 at some early time slice. Similarly here with the early time operator phi of x1 at some late time slice. Then I have to compute the overlap of these two states, and that's a scattering amplitude I have to compute in extremal BTZ. So let me give you some intuition of what to expect, because we saw before that in non-rotating black holes, the iconal phase was simply given by Mandelstam S, which is related to the center of mass energy. So let's compute the center of mass energy first in rotating BTZ, and then we'll specialize to extremal maximally rotating BTZ. So let's consider infalling and outgoing geodesics, which if the operators are inserted close to the boundary will be almost null by the time they reach the interior. And let's assume they cross at some radius r star. Each of these geodesics has some conserved energy E, and for simplicity, we take them to have 0 angular momentum. So then Mandelstam S is given by this expression. So what matters, apart from the energy of the geodesics, is the value of F evaluated at the interaction radius. So we have the expression for F here. So I want to translate this F of R star into the time difference between the early and late time insertions. So to do that, you write T of an insertion minus T star as an integral dr over F. So I've repeated the main formula here. So this will be dominated if R star is close to the outer horizon by the following integral by the region close to the horizon. And in the regime where R star is close to R plus compared to the distance between the inner and the outer horizon, this behaves logarithmically in R star minus R plus. There's another regime where the two horizons are close to each other compared to the interaction point, the distance between the interaction point and the outer horizon. And in that case, F behaves quadratically in R minus R plus. And if you integrate it, you get 1 over R star minus R plus. So if I now translate F of R star into a time difference, I find different behavior in the two cases. In the first regime, I reproduce the exponential growth as a function of time. In the second regime, I get quadratic growth as a function of time. And so the first regime is what we saw before for non-rotating black holes. The second regime is similar to what we know from slow scrambling. Notice that in the extremal limit, the first regime disappears, and we're always in this regime of quadratic growth in time. So this is where we are.
Ben, I had a question. Is this some way to get this intuition from the geodesics from the time of flight? Because okay, I understand the one in the extremal one, and I understand the log of r minus r star. That's clear. But I'm just wondering, how do you go from there to this delta t squared?
The delta t squared comes from the second expression here, right? So this regime is the same as this. You can see my cursor, right?
Oh, yes. Yes.
So this regime is the same as here. So okay, I should go up, I guess. So t minus t star is this integral. So t minus t star is 1 over r star minus r plus. So you should, okay, where are we? So this s, okay, I should go back here. S was given by 1 over f, evaluated at r star. So, okay, so I should take this 1 over f, and then I should replace this r star minus r plus, which will be here, by this, and this is the time difference.
Hello?
Yes.
I couldn't hear the last. This is the time.
Okay, let me back up. So, okay, so I want to replace f of r star by a function of the time difference, right? So to relate r star with the time, I will use this.
Very good.
Yes. So I will now compute this integral. So this is, and this is the regime we're interested in.
Yes.
So this time difference here is related to r star in this way.
Good.
And then I should evaluate f at r star. So this will be dominated by
the second guy.
By both, because no, this is rotating. Sorry, this is where they're close together, so I can approximate r plus and r minus as being the same.
Okay,
so this will,
is the extremal.
So that's where you get the square. So you will get r minus r plus times r minus r minus. So that's r minus r plus squared in this regime, and so that's how you get the square.
Okay.
Okay. So okay, so here we are. So S, well, here is the reasoning actually, goes like delta t squared. So as I mentioned before, in the exponential Lyapunov regime for non-extremal black holes, we used to have that the iconal phase went like g Newton times S. And in the slow scrambling regime of extremal, we will find some additional time dependence, which I'll come to next. So our guess based on what we saw so far would be that the exponential is replaced by delta t squared. We will actually see that the final result will be more like delta t cubed up to some modulations, but that's what I will discuss next. So to compute the TOC, we have to compute shockwaves of either of the two geodesics. So let's look at the outgoing geodesic. And the only thing to take away from this picture is that the shockwave is emitted towards the boundary of ADS. And so here is, well, using that as input, I'm not going to go through the derivation now. I will give some intuition a little bit later. But using that as input, you can compute the iconal phase delta. And here it's given as some contour plots. On the horizontal axis, there is delta phi, so the distance in the angular coordinate of the two insertion points at the boundary, or the two pairs of insertion points. And on the vertical axis, there is delta t. And This is what you would get if the angular coordinate was decompactified, or if you had, so if you had an extremal BTZ black brane instead of a black hole, if you wish. So if we want the result for a black hole, so in global ADS, you need to use a method of images, where now the fundamental domain of the angular coordinates is the more bright region here. And in faint colors, there's all the images which contribute to the contour plot in this fundamental domain. So to get some intuition for what is plotted here, I will give you two slices. The first will be the horizontal slice, where we fix the time difference between the initial and final pairs of insertions, and plot what happens as a function of the angular separation between them. And next, I will give a slice where we look at the time dependence for fixed angular separation. So here is the behavior of delta for a fixed delta t, so for a fixed separation in time between the initial and the final pair as a function of the angle. And importantly, the profile should be periodic because phi is a periodic coordinate. And there is a kink which corresponds to the geodesic that sources this shock wave, which I've chosen to be at the value of pi in this plot. If you look at the time dependence, which is the most relevant thing for our purposes, the result is given by the blue line here, which to a first approximation is well approximated by the orange dashed line, which roughly corresponds to a cubic function of time. But you see that superposed on that, there is this sawtooth pattern. And if you look more closely, the sawtooth consists of first some local quadratic growth, which is of course slower than the cubic growth of the orange line. But then there is some exponential growth that catches up with the cubic growth, and then it starts again. So you have some sawtooth pattern superposed on a cubic average growth. So let me try and give you some more intuition for where this comes from. So first of all, since the angular coordinates of BTZ is periodic, we obtained a shockwave using a method of images. And importantly, for a fixed separation delta t between the early time and the late time insertions, the number of images that contributes is proportional to delta t. So this can be obtained from a simple causality argument. And so it turns out that this factor of the number of images combines with the delta t squared we had from the Mandelstam S of the scattering amplitude into an overall cubic growth of the iconal phase. So then what are these local quadratic and exponential regimes? Well, these precisely reflect the left and right moving temperature of extremal BTZ. The left moving temperature is 0, and this gives you the quadratic growth that we had from slow scrambling, which also happens in vacuum. And the exponential growth is precisely given by the right moving temperature of the extremal BTZ. An important point here, which also, which is at the heart of why we couldn't simply or couldn't in any straightforward way obtain these extremal BTZ results as a limit of non-extremal rotating BTZ, is that in the earlier calculations, it was perfectly possible to let the infalling out for outgoing geodesics propagate at the horizon. So in other words, one computes the shockwave as if it was on the horizon of the black hole. This no longer works in the extremal case. And the intuition is if you have some series where you get higher and higher powers of exponentials, then it will be the first term that dominates. Whereas if you're adding delta t squareds with various coefficients, the various terms will be important and they will add up. And that's why in this case, as opposed to the Lyapunov case, you get an extra factor delta t essentially from counting the number of images that contribute. So put yet differently, the two geodesics can interact via this like changing graviton essentially, but this can move around the circle a number of times before it's observed by the second geodesic. So this sawtooth pattern has been observed before for the case of non-extremal rotating BTZ in the large time regime compared to the inverse temperature, which is of course a very different regime from what we're talking about now. And then there's quite a few earlier papers on scrambling in rotating BTZ, which I mentioned at least some of them here.
And what sets the scale at which the relative contribution of these two growth patterns?
Yeah, that's it depends on the right moving temperature. So if the temperature is high, it means that the exponential growth will be very fast, and therefore you only need a small amount of time to catch up. So maybe I should go back. You can basically see it in, well, this plot can be translated in the other one. So there is the sharp part, which has to do with exponential growth, and then there is the slower part, which is more like quadratic. Well, basically the whole thing has to be periodic. So you have to compensate the longer slow part by a faster short part. So the higher the temperature, the shorter this part will be.
But doesn't the exponential always beat out the quadratic or something? So why is there even a quadratic phase there?
Well, by construction, the whole thing has to be periodic.
Yeah, no, I understand that argument, but it's just trying to figure out the relative contribution.
Okay, let's see. Yeah, I don't know how to explain it better.
Some kind of initial condition is being fixed somehow.
I think one comment on that is that in some sense you can think of it as the geodesic is sourcing some gravitational perturbation, and the exponential is like an exponential fall off of that perturbation. Whereas there's like, so essentially like on the left or something, the perturbation falls off like a power law, and the other side it falls off like a exponential. And so you get a sum over many images that add up on this long power law tail. Well, this picture is kind of, this is the result of summing over these images already. So it's a bit hard to see from this picture. But the idea is that, yeah, if you have this long power law tail, it can add up over lots of images, and that's how you have this accumulation of images on when you have these power laws, whereas the exponential tails kind of slowly fall off, and then you only see one image at a time.
I think I see. I mean, what you're doing is you've got a right moving wave that's growing exponentially, or sorry, vanishing exponentially. You've got a left moving wave that's behaving the power law, and then you're sampling it at a point somewhere on the circle, and sometimes you're close to the quadratic, the power law source, and then you start approaching the exponentially decaying source, I guess. And
yeah, exactly. Yeah. Well, that's it. But the power law can go around multiple times the circle before it kind of vanishes enough. You know, it's just that when you get close to the source on the right side, you're sort of sensitive to this exponentially decaying part, like you say.
Yeah, another observation, I'm not sure if it will help, is that so you have a sum of two terms, and if you look at the function themselves, it will be the slower part, in this case the power law, that will dominate. But if you look at the derivative, then at some small regions in delta phi, the exponential will compete in the derivative, and that's these small regions where you see its effect, even though you would naively think that it has a small coefficient in front of it. But okay, I'm not sure if this helps if you don't have the formulas in front of you. All right.
Ben, can I also ask?
Sure.
Does it make sense to take the mass as limit here, and would that just kill the exponential growth and make it a quadratic? Yeah.
Yes, then you would go back to the slow scrambling in vacuum, right? Yes,
okay.
that's correct. Okay, so that was my discussion of OTOCs in extremal BTZ. So now let's try and make the connection with microstate geometries. So this is something many or most of you know much better than I do. So let me be very brief about the setting. I will be talking about the so-called 10N superstrata. All you need to know about it is this picture of a spatial slice where if you took away this cap region and let it extend to infinity, you would have maximally rotating or extremal BTZ. The difference is that this geometry, because of the interplay with the higher dimensions, is allowed to cap off smoothly at a certain radius. So this geometry is horizon free. There are some important radii to be distinguished here. There is the throat region, which separates the asymptotic ADS3 region with the ADS2 times S1 throat. There is the region which the radius rho cap, which separates the cap region from the throat region. And then there will be some radius rho tidal, which I will mention in a minute. So A will be a small parameter for us. It's discrete, but it can be taken small so that this can be a good approximation to what in this program is called the naive BTZ geometry. So these geometries have dual CFT states. They correspond to explicitly known states in the D1, D5 system, which has a large central charge and 6 times and 1 times and 5 numbers of D1 and D5 branes. The solutions are supersymmetric, so they're BPS states. They can be constructed at the orbifold point in moduli space. And they're constructed by adding momentum in a specific way to charge solutions and decreasing the angular momentum at the same time. And so these parameters A and B are related to the angular momentum, which we'll take to be small, and the momentum of the D1, D5P system. So, okay, so let's take this geometry instead of extremal BTZ and let's see what changes in our computations. So, well, first let's map these special radii into time differences of the insertion points, which are such that the interaction happens at the radius we're interested in. So for instance, for this rho throat, I'm asking what is a time difference I should choose on the boundary such that the interaction between the two geodesics happens at this radius. And the result is that this is given by the inverse of the right moving temperature. For the cap region, you will obviously have to take a much larger time difference in order for the geodesics to probe this deep in the geometry. And delta t of this transition to the cap is given by 1 over TR times N1 and 5, which is a large parameter. So what is clear, even without doing the computation, is that if the throat is capped off, also the center of mass energy will be bounded, because you cannot have arbitrarily large blue shifts in this case. And that's indeed what you see if you compute Mandel's time S as a function of the time difference between the early and the late time insertions. So that's one straightforward effect. The second effect that one should, in principle, compute if one wanted to be more careful than we have, is one should, in principle, take into account that even though outside the cap region, the BTZ shockwave can be used because the geometry will be very well approximated by BTZ there. Once you enter the cap region, you need to be more careful and you will need to use the 6-dimensional superstrata geometry that underlies this 3D picture. This we haven't done yet. We think it may well be possible because of other work in the Saclay and related group, which has been doing similar computations with geodesics before, but we haven't seriously tried. Another effect I want to mention very briefly, and which again was studied in much more detail in the Saclay group, is the tidal forces that might invalidate the geodesic approximation that we've been using. So that's also something one should in principle worry about. So in our geodesic approximation, we replaced the propagator by an amplitude times a phase factor. The phase factor is given by an action, which is just the length of a geodesic. And validity of this approximation requires that the variation of the amplitude is slow compared to that of the phase. A necessary condition is that if I take the derivative in along the geodesic of this amplitude, it should be small. And you can compute that this derivative is given by in terms of this volume expansion. And if you put everything together, a necessary condition is that this theta should be small compared to the mass of the particle that is being scattered. This theta satisfies the Raychaudhuri evolution equation. We've not studied it very carefully. We've focused on this last term, which in a superstratum geometry has two contributions. One that is already present in extremal BTZ, and which we're not going to worry too much about. But then there's a second term, which is only present if this parameter A is non-zero, so if there is a cap, and which grows as a row gets small, so as you go deeper down the throat of BTZ. And if you verify, assuming that this term will dominate, you see that the geodesic approximation is invalidated at some time scale delta t tidal, which is given by this expression. So what we've done is compare the various timescales that we're talking about, because on the one hand, as long as everything happens in the BTZ region of the microstate geometry, you can safely take our previous results of extremal BTZ and say that they're valid for these microstates. So you only expect deviations when the scattering happens in a region where either the cap or the tidal forces will modify the computation. So let me give you the result of that exercise. If you compare the scrambling time Ts, which is the time at which the OTOC saturates, with delta T cap, you get the following ratio. And the conclusion is that almost all the factors on the right-hand side are trying to make delta T cap large compared to the scrambling time. And this means that the scrambling is unaffected by the presence of the cap. And so we can safely take the BTZ results. So this sawtooth pattern on top of a cubic growth in time. You can avoid this by taking the right moving temperature extremely high. And in that case, you would already find interesting deviations due to the cap before the scrambling is finished. Similarly, you can compare to delta T tidal. And again, similarly, most of the factors on the right-hand side are trying to make this ratio very large. So usually scrambling happens before the tidal forces may invalidate the geodesic approximation. Again, an exception would be to take an extremely high right moving temperature. So, okay, let me end by a very brief summary. We've seen that the Lyapunov behavior of OTOCs can be related to gravitational scattering near a black hole horizon. That was review. And also that an OTOC can be computed using geodesic approximation. In extremal BTZ, which was the topic of this talk, we saw that the gravitational scattering happens away from the horizon, and that was crucial. If we had taken the near horizon limit from the beginning, we would have found infinity instead of cubic growth. We found slow scrambling, so cubic growth instead of exponential growth. And we saw that the OTOC displays a sawtooth pattern on top of that average cubic growth. In the microstate geometries, well, they mostly reproduce the slow scrambling properties of extremal BTZ because deviations only kick in after the scrambling time, except at extremely high right moving temperatures. And so, at least for me, the next step is to try and reproduce and understand as well as possible these features, in particular the sawtooth pattern, in particular in the extremal BTZ case, from doing CFD computations that would generalize the results of Robert and Stanford I started from. That's work in progress. There are some things we've understood, there's other things that remain to be understood, but well, in view of time and incomplete results, let me end here and see if there's any questions. Thank you very much.
Thank you, that was great. Okay, guys, been quite a few questions, but there's plenty of time for more, so who wants to kick off?
I have a question. Sorry, Emin, go ahead.
Yeah, lots of questions. So,
Yeah.
So how? I haven't had my coffee yet, so I'm not terribly coherent. So how far down the throat can you go? Can this R star be before things start going haywire? So there's this sort of like characteristic, geometric mean scale where the tidal forces become large. It's like R of order root A times B. Is that playing a role here at all?
Yeah, so
that's his row tidal, isn't it?
Yes, that should be the row tidal. So we computed when this, so at some point there will be this Planckian contributions here where you will expect that this condition will be violated. So that's what we took as row tidal, and then we translated this into a time separation.
And so for time separations larger than that, things start going haywire.
Yes, then you start being sensitive to the region with strong tidal forces. So at least a priori, we cannot trust our computations based on geodesic approximations. And then, okay, I guess you and Nick and others are the ones that maybe have some intuition of whether it's really bad or not so bad. I think in my talk from a few weeks ago, Nick was saying, well, maybe it's not as bad as we first thought, but there I don't have anything to add to what you guys know.
Can I ask a stupid question about just the dimensional analysis? I was trying to, that formula in the middle of the slide we're looking at, it's 1 over b. I was expecting a squared b squared over r to the 6, and then the left-hand side is dimensions of 1 over length squared, but somehow there's an extra factor in here that I don't understand. It's
okay, we're setting LADS to 1. That may be one source, but I don't know by heart.
Anyway, that row to the 6.
If it's not a typo, yeah.
That's the multipole moment that drives the tidal force, so it's the same thing as the tidal force. So it gets large of order 1 when rho is root AB, I think is the point.
I think just one comment on this is there's the way we look at it is that we actually try to integrate the Riccier equation. So we're saying that like this right-hand side term gets large at something like there's gonna be something like a to the 1/3 and b to the 2/3, I think, or something like that. It's kind of like out of the throat a bit of the square root of the two of them, and then but it takes a bit of time for the integral to actually get to be order 1. And what matters here is like when it becomes kind of order 1, because we're comparing it to the mass here and not to the Planck scale. So we actually, I think that, like it's very similar to the calculations you guys were doing, but it's a slightly different in details just because we have a very particular condition here we're looking at, and that's the one we were like focusing on.
Yeah, I was curious about this because I also remember that from Emil's my calculations that there were two eigenvalues to the tidal force, which when you add give you the Raychaudhuri or Ricci scale apart. And I thought that one eigenvalue was positive which went like n squared, and one was negative, went like n squared. And I thought the Raychaudhuri equation would only be linear in n, but that was, you know, maybe misremembering things.
I think we looked at the full deviation equation, which would have like the Riemann tensor times these deviation vectors, and the components didn't seem like this seemed to capture the scale of the components of that.
Okay.
So there, I don't think we didn't see any other we weren't too worried about having to look at the shear and other terms, let's say, of the type of expansions you could get. But
yep.
What is epsilon in this formula?
It's the UV cutoff of the holographic dual of the
okay.
Like the UV, yeah.
Yeah, that's why we're inserting the operators, I guess, in the bound.
Yeah. Like the boundary cutoff radius in 1 over epsilon.
So Emil, I think it's sort of similar to what we were saying in a subsequent calculation that yes, the tidal forces get very large at root AB, but they're integrated effect because it's traveling ultra relativistically and so fast. It takes a lot more distance of falling down the throat in order for that to make something grow out of control. I think that's what's being said.
Yeah, there was a similar, exactly. Yeah, I noticed that said, yeah, in the most recent paper, right, or the one that came out around the same time, just before we did it. Yeah.
I should stop dominating this, and, since I'm supposed to be mediating. Please keep going with the questions. Emil, did you want to follow up?
Yeah. So okay. So I guess another question has to do with the interpretation of this in terms of scrambling. So because I mean, as a calculation, it's sort of you know, 2 shockwaves come in, 2 shockwaves, and basically then they scatter off of each other, and then they reconstitute 2 shockwaves that go out. So it's more like so. I guess I'm confused. Maybe it's a question for Roberts in Stanford or Schenker in Stanford as to why this is reflective of scrambling. I guess I sort of understand in the case where there actually is a black hole horizon present. You know, there's some story about you know, shock distortions of the geometry, but well, let me stop babbling and ask what you're got these calculations fresher in your mind than I do. Why is this? Why does this tell us something about scrambling into microstates?
Oh, that's scrambling. Okay, so I was more thinking in terms of operator spreading. So scrambling in the sense that if you start with some localized or information in some local operator, that if you wait some time, it will be scrambled over the system, so it will be delocalized. And to make that link, you talk about the commutator squared and link it to the OTOC, and then, well, that's the reasoning I made in the talk, right? So, but I guess you're talking more from a perspective of transitioning into other microstates, or is that your take? Or?
Yes. So you say it's not really probing that sort of scrambling.
Not explicitly, but that's not what we had, at least what I had in mind when we were doing these computations. I was more coming from the commutator squared OTOC Lyapunov story. I can't exclude that there's an alternative interpretation along the ways you're suggesting. I'm not sure.
So isn't maybe I'm being very naive, but isn't that the point that you know, you're looking for exponential dependence on initial conditions? So you scatter 2 things off each other, and you want to know whether that scattering process has a runaway exponential that cuts in and then just that cuts in on any deviation on the initial data. And I thought that was what this calculation was to some extent about. You know, you're looking for that exponential growth is supposed to be, you know, the loss of information created by chaos, a chaotic phenomenon, which is...
Yeah, it's sort of the initial stages of thermalization. I thought that was the interpretation that was being given.
Yep. So that's, I think, the calculation he's doing, right?
Can I just, I think, like as Ben is saying, the statement is about operators though, right? Like if you imagine being in an eigenstate and you time evolve it, you're never going to go to another eigenstate if it's a true eigenstate of your system, right? But it can appear to be thermal because operators that you know, if you evaluate local operators in that eigenstate, they'll see something that looks like a thermal, like the local density matrix maybe is something that looks thermal, or all these ETH type ideas, right? So this is kind of probing how the operators see the microstate.
Stam's got his hand up. Do you want to jump in?
Yeah, let me take my hand down.
Yeah.
Let me take it down now. Yes, I have the following question because, first of all, about just to go on with the discussion at this point, is it therefore correct to conclude that despite the fact that this system does have a finite temperature because TR is non-zero, nevertheless, the probes don't thermalize if there is so slow scrambling? That's my first question.
Well, okay, I guess the way I'm thinking about scrambling, but there may be a language issue, is in terms of spreading of information in space. And so in other words, if you start with some local operator somewhere and you have some local operator somewhere else, initially they won't talk to each other, but as one of them spreads, it starts feeling the other one at some point. And by the time that happens, the information about the operator has spread in the system up to that size. And I would say that does happen also in this case. It's just, okay, it may be slower because there's no exponential growth. It's only power law. But I would say that slow scrambling is also scrambling in that sense.
And my second question is also, if the fact that this is an extremal black hole, but nevertheless it does have a temperature, there is a temperature, a non-zero temperature for one set of modes. Here it's by convention the right ones, the right moving modes. Is that a special feature of the BTZ extremal black hole? Because I would have thought naively that if I have an extremal black hole, the temperature, there is one temperature and this temperature is zero at extremality. That's one way to define extremality. So I'm just wondering whether this is something special about BTZ.
Well, we're talking about 2D CFT, so I guess you will automatically end up with BTZ. So in that sense, okay, let's see. Is there some higher dimensional analog? I guess that could be a question.
That's right. The Hawking temperature of this black hole is zero, right? I mean,
No,
yes.
Okay.
There is a temperature and it's zero, but then you can decompose that in terms of left and right moving temperatures. And
Exactly.
I was just wondering whether it makes sense to take another limit in which one sets T left equal to T right. They may be non-zero. If T left equals T right, but it's non-zero, it's non-extremal. But if T left equals T right and then both tend to zero, is it correct to say that one gets an extremal BTZ?
Well, then you get just a vacuum, right?
You get global ADS. Stan, it's basically what's happening here is you've got a left-moving CFT and a right-moving CFT. This thing is BPS in the sense that the right-moving, or maybe it's the left-moving in this convention, but the left-moving is in the Ramond ground state, and the right-moving, the other sector, is in some excited momentum state. But that excited momentum state can be assigned a formal temperature, and that's
because it's a momentum state.
Because it's a momentum state, it's got excitation. And so it's the weird thing about 1 + 1 dimensional CFT. One sector can be 0 temperature, the other sector non-zero temperature. If you put both temperatures equal and set them to 0, you've just killed all the momentum excitations and you're back in D1, D5.
But don't you keep the winding modes?
So there's no other modes. It's
Can't
just
you not keep the winding modes if you freeze out the momentum modes?
so it's just D1 and D5 wrapping a
Yeah,
torus.
that's right.
But it's
extremal BTZ, isn't it?
oh,
Sorry, it's zero. It's not extreme. It's zero. It's the non-rotating extremal geometry, right? Pointer.
I guess
have naive system which is useless, which doesn't have, which is just a wrong geometry. It doesn't correspond to any CFT state.
we should.
I guess there's many Ramon ground states, right? So depending on which one you pick.
But the geometry you're looking at. So if you just turn off the temperature, if you turn on both the right moving and the left moving temperature, and you insist on spherical symmetry, you get the naive D1, D5 solution, which is singular. And also, you know that that solution doesn't correspond to any CFT state. Any state
But doesn't that get cloaked in a way that was discussed by Yatish, Doublecar, and collaborators?
Not in this particular system, not for the D1, D5. In the F1P system, it is cloaked, but there are some arguments by Sen that in the D1, D5, somehow the cloaking doesn't happen.
Always.
And also, if you work on a torus, there's no cloaking at all. If you work on a torus, I mean, essentially, that's what I understand. But again, maybe people.
I'm just asking just to.
Yeah, but there's the important effect here is created by this high redshift in that's intrinsic to these geometries. And without the high redshift, you're not going to get any of these cool effects. And that means you have to have a large momentum state in the left moving sector or the right moving sector. And that means you've got a temperature in that sector.
Indeed. I just wonder how free are you to exchange the momentum states by winding states? And apparently, so the statement is that you're not.
Do you mean the winding states of the string or winding states of?
Well, of the D1, D5 of the D1, D5 system, or the D-brane construct, the D-branes that are wrapping around that do provide the additional states along with the momentum states. I'm just wondering whether for the BTZ, there are the special properties of the BTZ that say that you don't have this freedom that you would naively think that you would have.
I'm not sure.
Just asking. I don't.
Okay. One last quick question. You said that you start feeling the cat when the T right is high. Now, if I remember rightly, T right is something to do with N. But what in the CFT, in terms of the CFT states, does T right being high mean in terms of seeing something interesting in the effect of the cat? Just in terms of what are you doing to the CFT states to actually probe this T right being large?
Yeah, I don't know. I mean, okay, so here is this right moving temperature. So at least naively, it looks huge. So I don't know. Actually, I don't know if there's any bounds on T right. I mean, I'm not aware of any upper bound or.
T right is N, isn't it, or something like that? If I remember.
Right is NPS, the number of momentum quanta. There's no upper bound on it.
Is it really N or is it? I thought it was
NP,
N.
The number of the momentum.
Well, I don't
It's
think
that little n, right?
It's the little n. It's not b squared little n. B squared little n is QP.
Ah, b squared little n. Sorry.
I mean, b is somehow dimensionful, right? So, I mean, the way we were trying to think of it anyways was that n you can sort of tune, and then b was essentially giving the ABS scale.
Yeah, right. N is T right. So this is saying something like that the L minus ones you're acting with, there's a huge number of them. So it's some really strange.
I mean, you notice there's like the cutoff in the denominator there, right? So you have to also work with like a finite cutoff in the bulk and so on if you want.
Yeah. Okay, so it's probably some insane CFT state.
No, but I mean, this is a Cardi state, right? I mean, that's what you're doing in a Cardi limit. In a Cardi limit, you're basically putting a huge momentum. You're putting.
No. You're distinguished. You've got to distinguish. I think T right is not the momentum. I think it's the number little n, if I remember rightly.
But I think they're proportional. I don't think there is.
No. There's a b squared, which would change everything. Is it b squared n or
no, b squared just said yes. I mean, if you compare numbers to numbers.
Yep.
So compare. I think it's okay. The Cardi limit is the number when the number of momentum quanta is bigger than n1 n5. That's the only limit which I can define in this theory. So
no, there is another limit, which I think is what this is all about, which is when little n, which is the L-1 operator acting little n times on the state, is some insanely large number, I think is what this is.
compared to n1 n5, but that's the Cardi limit.
No, b squared n is QP.
No, the Cardi limit is
NP is given by b squared n.
No, NP is a number. QP
Yes.
is given by b
Okay,
squared.
n squared, b squared n divided by all sorts of crap to do with the volume of the 4 torus and alpha primed is NP. And that's b squared n. And I think this is not the Cardi limit. I think this is something else.
So
Well,
what's
that's what,
happening
that was
in
what
this
my question. That was really my question.
No, I'm confused. What is happening in this limit? I'm very confused about this limit. I've never seen it before.
Yeah,
I'm
that's
trying
right.
to get some intuition of what's happening in the geometry in this limit. I don't know.
Indeed.
Ben, if you have some.
Well, yeah, I don't have more to say than what I said, in the sense that if you take the well, you take these two geodesics, and that's when they start probing the cap region of the geometry. So, well, that's where. Okay, how should I say it? That's where at the scrambling time, at the separation corresponding to the scrambling time, the geodesics probe the cap region.
Right.
So usually this only happens for time separations much larger than the scrambling time, because the cap is so deep down the throat. But if you go to this extremely high temperature, then already for time separations of order the scrambling time, you feel the cap. That's the interpretation. But if there's another interpretation to it, I'm not sure.
Okay, in the interest of avoiding Zoom fatigue, I think we do need to take a 20-minute break. I don't want to start out by running too long into the break time. So, Joseph, let's stop the recording, but we'll leave the link open and people can talk, but there's going to be nothing more formal said